All right, let's get started. Good afternoon, everyone. So today we're going to be talking about forecasting methods. So a lot of sort of systems modeling, we're often thinking about, problems in the future, and in some form of another, that's almost always going to have to sort of bake in some types of assumptions about what's happening in the future, and forecasting and how that gets layered into modeling. And so we're going to spend a little bit of time today kind of explicitly talking about different ways that folks do forecasting, and essentially how we can do this in kind of a smart way, right? So the idea is we are making some sorts of predictions, but we're doing this in an informed way, right? And so we want to use past and present data in order to, make these predictions. And the form and the mechanics of doing a forecast can vary, right? We're going to talk about different techniques to do this, but in general, right, we're not just kind of pulling things out of thin air, right? This is an informed process. The other thing that I would try and distinguish is thinking about like a short-term versus long-term forecast. And I say that as a more sort of generic kind of approach to this, but really what we're thinking about is how the length of the forecast really influences the sort of approach that you might take. Right, and so what differences are there between short-term and long-term? What sort of assumptions might be a little bit more stable in like a shorter-term forecast versus something that maybe we would want to think about a little bit differently in a longer-term forecast? And then, what types of forecasts are more or less certain, right? So what do you guys think? Is a short-term forecast more or less certain than a long-term? More, right. So oftentimes the farther we go out, often the uncertainty around our outputs and our predictions are going to sort of increase. And we've covered sensitivity and uncertainty. And so as you do these types of things, definitely make sure to incorporate that, right? Show that there are more uncertain outcomes in these sort of longer term forecasts. Right. How might forecasts change over time? The way in which we kind of update our forecasts and we intake a lot more information every year, that can lead to pretty drastic changes in what we think will happen in the future, right? And so this is like an example of this. So Bloomberg New Energy Finance, they had a forecast in 2015 that said, over the next, a couple decades, by 2040, we would have 46 million electric cars. And then just a year later, that forecast changed by, almost an order of magnitude, right? And so we have to think about, as we make these forecasts, how new information can possibly sort of drastically change our outputs. And that's why it's also important to include the sort of uncertainty, right? Because maybe it's the case that if you just change a couple of parameters, right, maybe you have these really big error bars. But in this case, that's not shown. But I would encourage that we do that kind of practice. Okay. And forecasting is really hard to get right. On the left-hand side, there's a plot from the Energy Information uh, agency, yes, the EIA. So the EIA is a federal agency that does a lot of sort of energy forecasts, and they actually use some systems models that we're going to talk about later on in this course to do that. And so every year they publish a new set of forecasts. This is particularly coming out of this big modeling effort that then gets sort of aggregated out and pushed to the public, and that's known as the annual energy outlook. And one of the things that they do is they forecast prices for fuels, right? And so you can see every year how that's sort of changed. And so, yeah, this goes all the way back to 2004. And you can see every year they're like, oh, the next year they update the forecast and it changes quite a bit, right? So the magnitude of these changes is anywhere from like $5 all the way up to like $12. So, you know, a 2x difference in magnitude of what they think the prices will end up being. Well, what happened in the 2000s with as it relates to natural gas? Fracking, yes, exactly. And so that really changed the supply and the sort of corresponding prices of natural gas. And actually you can see this plot here on the right-hand side is a graph of historical prices. So these are not projections, right? This is like what actually happened. And you can see, you know, for a period of a decade, it was, you know, $4 or below, whereas not a single one of these projections, you know, all going from 2004 to 2011, got any of this right? Every single one was overestimating this time period, which is reflecting kind of this same amount, this same time. Yeah, so this stuff is hard to get right, especially when you have like big disruptions where we might say something is changing in a more sort of revolutionary way than evolutionary way. But that doesn't necessarily mean that those forecasts and those predictions are useless, right? Understanding the assumptions that go behind them and the drivers behind particular outcomes is going to be maybe just as important in understanding, you know, your system compared to just looking at the outcomes. Okay? So don't worry if you get your forecast wrong, because everybody does. Okay, so today we're going to look at a couple of different approaches to do forecasting. We're going to look at a couple of sort of time series methods, trend analysis. So this is going to include things like some simple regression models, decomposition models, which I mean, these are all technically still regression models of some kind. Yeah, we'll look at ways of doing this in a more structural way. And then we'll look at a couple examples in a more sort of simulation and use engineering analysis. And actually the latter one we may touch on later on in the course as well. Okay, any questions about this so far? Great. So regression, who's taken a class in econometrics or regression of some kind? Most folks? Some folks? Okay. So this is a statistical process for understanding the relationship between variables that given data about those variables. Okay, so hopefully many of you are familiar with linear regression. So just from a sort of methods point of view, we'll walk through this really quickly. Y is our response variable. We have our x's as explanatory variables. You may also hear these called dependent variables and independent variables. I don't like that terminology, but you can take a different class to find out why. You have coefficients that describe the effect of your explanatory variable. And then you have your error term, which is anything that affects y that you're not capturing in your x variables, right? And so in a very simple way, right, if we were just to have a single x, then beta would be describing what? Not a trick question, like in a plot, right? If you have a relationship, yeah, it's just the slope. Yeah, and you can have a constant term in here as well, which I didn't include, and that could be an intercept. And then as you have sort of multiple dimensions of these things, essentially, right, what the slope is describing is the relationship between your x's and your y's, right? And so as you alter your x input, then your beta will tell you how much y changes. And yeah, linear regression is a sort of very common and simple way of sort of extrapolating effects. And you do have to be careful in terms of thinking how you're doing the prediction and whether or not the ranges, so especially if you're doing forecast, if you're making assumptions about what happens to your explanatory variable out into the future so that you can see how your response variable changes. If you are straying out of the range of where you've calibrated your x's, then yeah, you may be worried that that's not actually how that behavior would look outside of your sort of calibrated range. So that's one thing to sort of keep in mind if you are using linear regression for forecasting. Okay, any questions about this? I'm kind of doing this at a pretty high level, assuming that folks have been exposed to linear regression, but if not, now's the time to let me know and I can talk about this in a little bit more detail. Okay. So we're gonna build off of this a little bit in thinking about how to explicitly incorporate things like time into these systems, right? And so linear regression as a tool is kind of the foundation for doing some of this stuff. And as we think about forecasting, time series methods is particularly salient in this area because we're thinking about things in the future and we're thinking about how that relates to how specific things change in time. And so we want to use that information to essentially make sort of better predictions. So time series forecasts are techniques that utilize historical and current data to predict future values. Okay. So one of the sort of basic approaches in these sort of linear regressions, so we can think about an autoregression model. And so we typically use this to represent a sort of time-varying process. And the idea here is that a particular outcome may be related to what it looked like before, right? And so can anyone give me any examples of this um, where your ability to predict things in the future depend on what something looked like in the past? Yeah.
Like water demand? Or
Sure.
something?
Yes. Yeah. And so anything that's sort of transient over time, you might say something like, "Oh, I see this pattern of, let's say, water demand or water consumption happening. I can use that information and represent that in like a time varying process." Yeah.
The demand of a certain product based on like historical prices.
Yes. So I would. So for the purposes of this particular thing that we're talking about with autoregression, we're just thinking about the relationship to itself. You can fold in other variables like price, but that's like a slightly more complicated model. But the idea is, yes, like even without understanding something about the price, which may, let's say that may end up adding to like an average slope to something like this, the overall trend in like a demand, yes, oftentimes you could represent that in like an autoregression, right? And so just to be extra clear about the specific distinction I'm talking about with this example, so that would be something like your x would be a demand in time t, and that is directly related to the demand that you saw in time t minus 1, and then in time t minus 2, and so on and so forth. And then the extra layer that you would add if you're saying, well, it's not only related to the previous demand, it's also related to the price. You could add in a variable showing, oh, it depends not only on what my demand looked like before, but also on like a price variable. You do get into, some interesting, from like a methodological standpoint, there are interesting things happening there where you're folding in, if you have plus like a price at time t, well, actually, if I look at how I calculated x of t minus, so I should say, you actually automatically capture through this autoregression the effects of price in all of the previous time periods, right? Because what ends up happening is if I say, I don't have a, if I say plus my price variable, if I go back and look at xt minus 1, I can plug that in over there, and that would equal the sum of all the previous terms, but also plus the price at t minus 1. So depending how you set this up, you can actually sort of automatically account for things like that. And the main idea, if you want to explicitly include it, because actually your t minus 1 and so on and t minus I, since they sort of automatically include all of that stuff, the only reason you would include a separate variable is if you wanted to know the like effect of that particular thing. Okay? But yeah, that's a good example that gives us some intuition on how to include other variables in here. Not as controls, but as explicitly things that you want to find out more information about. Any other questions or comments? Yeah, great. And so there's a question of, how much lags or how far back essentially do I look, right? And so that's this p parameter, which represents the number of time lags. And that's something that you can kind of play around with, and you want to essentially balance between sort of getting better predictions versus overfitting your model, which we're not going to talk about the details of that in this class. If you're interested, you can take my data analysis class next quarter. But that's one thing to keep, to be mindful of when you're doing calibrations of your autoregressive models. Okay. There is a different style of time series methods known as moving average models. And so this is oftentimes kind of an alternative to autoregression. And actually, before I jump to that, did want to kind of look at this really quickly. So just so you guys note the difference, right? So we can see how forecasts for even pretty highly nonlinear things can get captured pretty well in autoregression. The moving average does it a little bit differently, where maybe we don't care necessarily about the variation that's happening, or the shorter term variation, and that depends on your moving average windows. But your sort of overall trend can get captured pretty nicely. So conceptually, you are measuring the current value against both the current and previous error terms, and so that's looking at kind of the noise. So moving average refers to, so moving average, and then you have parentheses parameter m. That m parameter basically is describing the window with which we're taking our average. Okay, and so the smaller the m, the larger the variability you capture, and then the larger the m, the more kind of smoothing that it'll do. So the actual form of this looks something like this. And you're always kind of looking ahead and behind when you're doing your calibration. And then when you move forward, you can essentially do predictions of your average based on kind of that mean value and what that looks like over time. Yes?
So how exactly does the moving average help me with forecasting? Because to me it just looks like I'm able to smooth this curve, but how do I use this for forecasting?
Yeah, so what you end up getting out of this are parameters that will describe how that curve is moving. So you do still have to make some assumptions about the way certain values are going to change into the future. But you can use the sort of calibrated coefficients out of this to essentially help you do that. Yeah, so there are other classes of smoothing models. So exponential smoothing models, these will capture trends and seasonality in data. And then ARIMA models are combining both the autocorrelations and the moving average models. And so once you're at a certain level of detail, it actually helps to be able to use some of the attributes of both types of models. And that's a pretty sort of common sort of foundational model in time series analyses. All right. Any questions? Okay, so let's talk about econometric forecasts. So econometric models attempt to quantify relationship between some parameter of interest, right? So this is our response variable, and a number of other factors, right? So these are your independent or explanatory variables that affect it. And so like the linear regression that I was showing you is one tool in the toolkit of like an econometrician who's trying to understand some of these relationships. This here is an example of essentially how GDP changes over time, right? And so the circles are the actual observations, and then there's a number of different sort of models, regression models that are fit against this data. And essentially what you can do is extend these models out into the future to be able to make forecasts. And the models themselves will give you parameter estimates that help you do this. Okay, but there's a pretty important concept as we think about these regressions. All right. So who can tell me what they think is going on here? What does this look like to you guys? We've got two lines. There's a black line that is in reference to the black axes and a red line in reference to red axes. So these are two things that have a pretty close relationship with one another, right? Would people agree with that or no? Yeah. Okay, so this is U.S. spending on science, space, and technology, and suicides by hanging, strangulation, and suffocation. So it actually turns out that the more we spend on science, the more people kill themselves. Yeah, yes, right. And so we come up with these, random things. So and I'm sure you guys have all heard of this, right? This idea about correlation versus causation. And the way that I think about this and frame these things is more on kind of an outcome, on kind of what we want as an outcome from sort of our models, right? And so in a more sort of prediction-based settings, really you don't care necessarily about the relationship between X and Y. You just care that you can describe particular outcomes given, some kind of input. And so what is the value of Y given X? It could be the case that there are some things in here that actually do cause these things to be related in some way, right? I don't know. Maybe it's this idea that academics, it's a tough life, but even though as we see the description here, even though it's like, oh, obviously there isn't like a causal relationship here, if this kind of relationship holds forever and you're in the prediction space, who cares? Like, I can use one to maybe predict the other with a high degree of certainty. That's likely not the case for this, but there could be, there could be other things. So the classic example that I give for something like this is, if I own an ice cream shop, one way that I can predict how well my sales are going to go is by going outside and looking at how many people are wearing shorts today, right? And that is not like a causal relationship between people wearing shorts and eating ice cream. But to me, if I just want to make predictions about how much like ice cream I need to stock, right? Then yeah, maybe I don't care about this causal inference piece of it. I just want to be able to make good predictions, and it turns out I have some good variable to be able to make that insight. And so don't, if you're in this world, then don't worry too much about the like causal piece of it. The causal inference part is like describing a sort of legitimate story about why relationships between variables exist and how that's backed up by data, right? And so in this particular example, it's not that people wearing shorts makes them eat ice cream, it's that it's hot outside, and people, when it's hot, you're more likely to eat ice cream, and you're also more likely to wear shorts, right? So in causal inference, we care primarily not about understanding how much ice cream gets sold, right? But let's say how things change as a direct influence of like outside temperature, right? And so what happens to Y when you change X? Okay, and so going back to forecasting, right? This idea about understanding whether or not we just want good values of Y versus if we want to understand the like causality of it depends on the question. And so there are some types of forecasts and systems where really you care more about the latter, and there are some that care more about the former, and oftentimes the techniques and approaches that we make to doing those forecasts is going to be different, okay? And so rather than describing kind of like the exact model, this should be for this thing, and this model should be for causality, maybe instead I will give a more sort of general advice about this as it relates to more kind of how it looks on a spectrum. So in a linear regression, we tend to use these types of models more to conduct causal inferences. And so why is that? Like, why do we continue to use, let's say, simple linear regression models, especially if you think about the field of like econometrics? And I am maybe simplifying this a little bit, right? But there are much more complicated sort of non-parametric models out there. There's like all these machine learning, deep learning models, right, that are doing all sorts of fantastic things. But why is it that this is still such a sort of used so prevalently in many fields? Does anyone have any ideas? Yeah.
I mean, it kind of says on the slide, like
Well,
the parameters are much more interpretable. Like if you have machine learning, you often just get like an output out of a black box, and you don't really know how you got there. And here you kind of know how the values are coming together.
Yeah, so that's exactly right. So there are these much more complex models that exist that oftentimes have like much better, predictive outcomes, right? But if a relationship is described by some crazy squiggly line, it's very difficult to make interpretations about how things will change and how certain things are influenced, because you might say, oh, from this range to this range it changes by this amount, from another range it changes by a totally different amount, right? And so in a linear regression, things are sort of much more interpretable. This particular example is just a model of regression results where I'm able to interpret how specific relationships come out. So this is a model from a paper that that I published many years ago that's looking at like how electric vehicle sales change as a result of having specific like tax credits and subsidies, right? And so we're able to make direct interpretations, and this is kind of like a model that's focused on causality. And so we can make direct interpretations about how our outcome of like vehicle sales change directly as a result of changes in a particular like policy. And these things are in general much more easy to describe in sort of linear regression types of models. Okay, and sort of as you sort of depart from that, as you go towards more semi-parametric and non-parametric models, there's a lot more structural flexibility, right? So not all relationships between our inputs and outputs have to be linear, or the relationships even between the inputs and the parameters have to be linear. And actually, we can, unless the actual relationship between two variables is a line, which not that many things actually in nature are, a lot of these models will sort of always produce better predictive outcomes. But a lot of those relationships are going to be essentially uninterpretable. And so there's a spectrum with which we're thinking about models that better address causality and models that are better suited to predict outcomes. And depending on the specific type of forecasting that you're doing, we're not saying that one model is better than the other, more that you should be aware of the sort of general tool set so that you know which ones make sense to use for your particular problem. Okay? So non-parametric models, so this could include things like kernel regressions, k-nearest neighbors, four-vector machines. These are just a random sort of set of models that I kind of pulled out that could be used for things like forecasting. But let's actually look at a handful of specific models. Okay. So one of the things that's handy about, or I should say in a lot of these systems models, one of the things that has arisen that is kind of handy is the fact that a lot of the relationships that we're talking about are common enough and have been used enough that, you know, there are sort of derived relationships that we can kind of fall back on to describe specific things. Okay, and so the first example that I'm going to talk about here is something known as learning by doing. You may also have heard of these as experience curves. And so this is kind of backed by economic theory, right, where your productivity and efficiency will kind of improve as production increases. And so to maybe focus on that theory part of it a little bit more, can anyone help me understand why that's the case, that productivity and efficiency improves? Yeah.
People get used to the processes and get faster.
Yeah, 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 exactly. And so, you know, what's the classic example that they do, like folding paper airplanes, right? Like the first time that you do it, you gotta like work out and figure out how to fold it, and then the more you do it, the faster you'll get at it, right? And so this this idea is essentially something that can get that is also sort of present in sort of general production of goods and services. And so we see this rough shape here. So as you produce more and more of a particular good or service, the time it takes to provide that good or service sort of decreases. And that's a relationship that can be described directly in this kind of form. And so this is actually a regression that you could actually calibrate data against. So if you knew a whole bunch of y's and you had a bunch of x's, you could actually calibrate the coefficients to understand how the experience curve actually looks for a particular good or service, right? And so the handy thing about that is because we've observed many products and services fall in this kind of shape, then I can take a new good or product. I can see, even if I have just a little bit of data to calibrate on, I can see what kind of the rest of the curve looks like. Okay. And so, as it relates to, let's say, specific, energy technologies, we can see, so this is a linearized version of the experience curves. They do still look like this, right? But these are by order of magnitude, so it's just linearized out. And so if I have, just a handful of points here, I actually have enough information to kind of forecast out what the cumulative deployment and in this particular case, the experience curve is describing the cost. It doesn't always have to be just the time per unit, right? It's also about like efficiency related to cost. So in this particular case, across many different technologies, you can see that the trend is essentially the same. Sorry, not the trend, but the sort of pattern of sort of decreasing in this exponential manner, right? And so because of this kind of well-developed phenomenon, we know that you can use a small number of observations to calibrate your parameters and then understand what how deployment in the future will affect your, in this particular case, cost. Okay, any questions about this? Yeah, so this type of relationship has generally held up pretty well across not just energy technologies, but most cumulative production of goods and services. So it's a pretty reliable one to be able to use. And so if you guys are trying to understand like efficiency of production, as it relates to the time or the cost of production, for new technologies, you can use this to do some, I think, pretty decent forecasts. Okay, so that is related to production. Our second example is in relation to adoption of technologies. So similar in the way that we've observed that there are certain things that happen in production that we can kind of emulate out into the future. There is a similar type of thing that we see happening with technology adoption that allows us to make some inferences about how that looks structurally. Okay, and so this particular example is looking at the percentage of households that use a particular sort of good or service, going from 0% to essentially 100%. And across a whole bunch of different technologies, and so we look at, let's say, electricity, this dotted black line, we can see kind of the shape of it looks like this, like a refrigerator, similar type of thing. And so what you should be looking at here is similarities in shapes, but not necessarily in like the slope, right? And so I'm going to show in a second how actually a lot of these things can be described with an equation that just changes the parameters that allows you to kind of alter the shape. But generally, you're looking at kind of an exponential growth first, and then kind of a decay towards saturation. And so we call that an S-shaped curve. And generally, for the most part, most technology adoption follows that shape, even if the sort of trajectory of that shape looks a little bit different. Any questions about this? Yeah, they're not going to be perfect, right? You have some, like, auto looks a little bit weird in the middle, but for the most part, I think you can describe most of these technologies as having this sort of S-shaped adoption. Yeah?
Can you describe this in reverse of like phasing out of the technology in favor of the new technology?
Yeah, I suppose so. I haven't seen that before, where people are looking at like
halogen bulbs versus LED bulbs, maybe? That could be phase out of technology.
I mean, it makes sense, right? If there are only two products, the other one is just minus this, basically.
yeah, but
I
that's
mean,
only
if
for
there are multiple products. then
yeah.
it's
It gets complicated, I guess, if there are multiple
not
products.
like with two-
But also, like, what would the auto be replacing? Like the horse and buggy?
Yes.
Yeah, it could be replacing a number of things, and then some things are like totally new, like a refrigerator. I'm not sure would be replacing anything.
Retailer?
The ice box.
The ice box?
Ice truck. That
Oh.
would drop off ice.
I didn't know that was a thing.
What?
Yeah, they had trucks that just drive around and deliver
Yeah.
ice.
Like
Oh.
Yeah.
Interesting. Yeah, cool. Yeah, I guess you could describe, yeah, if it's, especially if you're substituting for one direct product, then yes, like a 1- thing would likely describe that. But it probably does get a little bit complicated for some things. Okay, maybe not the fridge. What about?
Like a landline on a cell phone.
Well, I feel like cell phone would replace a landline, so that one would be easier. But what about like air conditioning? Was there an alternative to air conditioning before we had that?
Fans.
Fans? Yeah. Well, we still buy fans. Well, okay. Anyways, besides the point. So this idea that we generally have this kind of curve, and whether or not there's like a, disadoption curve, this falls out from what's known as theory of diffusion of innovation, which essentially is based off of like looking at all this data and seeing that, hey, actually I see this kind of similar pattern. So in this theory, the idea kind of describes this bell-shaped curve as kind of potential adopters in your population. And the reason why this curve kind of makes sense when you think about the cumulative adoption, right? And so this curve describes new people adopting the technology, whereas the curve we were looking at before, which is this curve in red, describes the cumulative total adoptions. remember, in an S-shaped curve, you grow exponentially at the beginning, and then you have an inflection point where you sort of taper off. And so that is kind of nicely described, right, by this shape, where you have growth in the beginning and then a fall off at the end. And then the theory describes the population and divides the population into like different categories of adopters, where you have like innovators. These are like the people who are sort of most interested right at the beginning, that want to, you know, adopt a new product. Then you have early adopters, early majority, late majority, and laggards, and so on, right? And so that,
Sounds like a slur.
what was that?
That sounds a bit like a slur, laggards.
Laggards? Yeah. So, yeah, anyways, this division is more of like a conceptual understanding of like different, separating sort of different portions of the population. But really it's meant to kind of essentially describe why we think the curve kind of looks the way that it does. Okay, why don't we take a quick break right now? We'll do 5 minutes, and we'll come back to the theory. All right. Let's continue on, or should I say, does anyone have any questions about this before we press on this theory? Okay. So now let's talk about sort of the application of how people have actually come up with models to essentially describe this behavior quantitatively. So our first example of this is looking at a sort of simple logistic model. And so logistic models are often used to describe these sort of S-shaped curves. And there's a specific equation structure with parameters that allow us to essentially draw this curve out. So this particular equation describes this sort of simple logistic model. And it's arranged in such a way so that I have a particular set of parameters that have been kind of designed to help qualitatively explain what's going on with this growth. So the first one is this parameter K, and that's your sort of maximum penetration, your saturation, right? And so the degree to which that's happening, that is essentially where you're leveling off, right? And so as time goes to infinity, you'll go up closer and closer to K, right? But it's a limit so that you never sort of quite reach it. Oh, and I should describe the actual outcome, right? F of t, that is your market share of a particular technology in time t. We have a growth rate that describes the percentage growth per year. And then we have a value, a static value, which is your share in your base year. And so where you what's your starting point? And then what year is that starting point? And then what year what year specifically are we looking for when we're investigating kind of the market share? Okay. And so oftentimes you can actually this particular equation is is particularly handy because it's so simple. You could actually describe with a particular growth rate and knowing what the K is, what the entire shape is going to look like. Even if you actually don't have these parameters, and you have data on like the sales of a technology over a couple of years, you can then conversely infer what these would look like. And so if you had a new technology, such as this one, where you only had data for this amount of time, you can take all of this, plug it in as a regression model, and essentially calculate what your K and what your R are going to look like. And so this allows you, based on some data here, to understand what's the maximum my technology is going to penetrate into the population based off of the sort of beginning data about that technology. So this is one of the reasons why if you have a new technology or service that's on the market, I'm actually able to make some conclusions about how far that technology is going to make it into penetrating your sort of general population. Okay, so a pretty handy tool, to do these forecasts. Okay, any questions about that? One kind of issue with that particular model is that oftentimes the like S shape of a logistic curve is symmetric on both sides of the inflection point. But that's not always the case for many products, right? And so we can see there's a few things where, so this shape is describing our sort of new adoptions, where sometimes the tail is like much longer, where sometimes it does look okay, but sometimes depending on certain things that might change as it relates to the technology or the policy, you may have new adoption curves looking more like in this type of shape. And so for that reason, back in the 70s, they came up with slightly different or alternative curve fits for new technology adoption. So instead of using simple logistic model, there's something known as a Bass diffusion model. And so this is still follows our sort of diffusion of innovation theory, right? So we still have this idea where some portion of the population wants to adopt it first, and then more and more and more, and then you have people who, a smaller portion of the population kind of on the tail end, who will adopt a technology later. So that sort of general shape still holds, but it's actually leading to a particular model that is a little bit more flexible in the way that that S shape is derived. Okay, so let me talk about the Bayes diffusion model quantitatively. So the way they think about this is there's a pool of M potential adopters. And so that M is analogous to the K value from the simple logistic model. And then they essentially just divide the population into two groups where we call innovators who will adopt the new products kind of on their own. And then there are imitators, which is the portion of the population that will adopt with some probability based on how many people are already using the product. And so the innovators have this particular parameter associated with them called P, and the imitators have a different parameter called Q. And those parameters essentially describe the rate at which, as an innovator, that I would adopt a new product, and as an imitator, how I would copy and decide on adopting something based off of how many other people already use it. Okay? So, your shape of your new adopters may look something like this. And that's, for new adopters, not cumulative. So the equation is a little bit similar in form and structure, but it looks like this with different parameters, right? So we have two curves here. So one big N of t, right, and that represents the cumulative population adopting a technology, and then and so that's using this left-hand axis, and then the right-hand axis is describing this line in green with lowercase n of t, which is describing the population of new adopters. And both of these lines can be represented in a set of equations. So cumulative adopters can be described as this equation, where the total M, and then you have this ratio between this 1 minus e to the negative p plus q times t over this term here. And then similarly, if you wanted to describe what this shape looks like, you end up with an equation that looks something like this. And again, these are just sort of sets of parameters that are qualitatively meant to describe, your adoption rate amongst your two population groups. Okay. Yeah, how is this useful? Well, the idea is that here, now all I need, the only really information I need is if I have enough information on like the sales or adoption of a particular technology in like a couple years, I can treat this essentially, this is essentially a regression where my parameters P, Q, and M might be unknown, right? And I can calibrate to those values, and once I have the parameters P, Q, and M, then I can estimate the rest of the curve pretty easily. Okay. In this particular example, you plug in a couple numbers from here, treat this as a regression where you're solving for P, Q, and M, and I can get this out of it, right? And so I have P is equal to 0.01, Q is equal to 0.15. And if you look in the literature, this particular approach has been applied to many, many different technologies, and they've extracted a whole bunch of like P and Q values depending on the different technologies, and you can look in the literature to see what that looks like. And like P's typically fall in some kind of range, and Q's fall into a different range. Yeah, and so this relationship is robust, right? Because generally most things that we found follow that sort of shape. And the main difference between like this and the simple logistic that I was describing before, right? We're kind of doing the same thing, right? Because in the simple logistic, instead of our PQs and Ms, we have our Rs and Ks that you might be calibrating to figure out what the rest of the curve looks like. The main difference is that unlike the logistic curve, right, there's a lot more flexibility in the shape of what that S shape looks like. And so the Bass diffusion model, is generally considered a more robust model than the simple logistic. Okay. Any questions about this? So I will say, the Bass diffusion model is a little bit older. This was derived, I think, in the 1970s. But since then, right, I mean, it's still been pretty heavily used, in a variety of contexts. A lot of energy systems modelers, a lot of transportation system modelers have used this to describe how new technology gets injected into a system. But one of the sort of drawbacks of this particular form of our Bass diffusion model is that you've got these like parameters P and Q, which kind of describe these like generic things about a population. But if I wanted to like inject certain things, certain variables into this model, so this kind of describes what happens in a vacuum when you introduce a new technology. But what happens if I say, I'd like to know what happens if the government decides to like subsidize a technology and put a whole bunch of money into R&D, or maybe they provide like tax credits if you purchase a technology. Or if there's something like revolutionary that happens in like another part of the world, and then a new technology is brought that like affects this in some way, right? This general relationship of the adoption can get influenced by some other things. And so people have actually come up with variations of diffusion models generally, but actually even more specifically with the Bass diffusion one, where, okay, maybe you're describing different shapes, like I'm saying here, or actually you're introducing other variables into the model. And so there's actually something known as a generalized Bass diffusion curve, which allows you to put additional, you like calibrate it to additional data. So you can see how things relate to maybe like price, for example. So yeah, just know that if you are interested in doing something like this for your project, yeah, I think a good starting point is the Bass diffusion model, but then just know that there are other tools that layer more complex things into it that let you, that are going to give you more flexibility to handle, you know, external influences on the technology adoption. Yeah, and so some criticisms of the diffusion models, some of which have been dealt with or folks have tried to deal with over the years, like the artificial restriction for symmetry and midpoint inflections, right? So I already mentioned that as it relates to the difference between like the logistic curve and the Bass diffusion. Yeah, a lot of these kind of assume that these diffusion processes are independent and they don't consider simultaneous diffusion of multiple innovations, which could affect the way something is getting adopted. And yeah, generally speaking, you are going to treat in these models most of these things as independent, unless you do some kind of generalized form where you're explicitly saying, okay, you have to like consider this other thing. Diffusion models are demand models and do not explicitly take supply restrictions into account. Okay, so this is a particularly important one, right? So all of those adoption curves that we saw are kind of based off of this idea that like the technology diffuses in a certain way depending on demands of the population. And so it is entirely demand driven. If you have weird supply stuff happening to a particular technology, that is not going to be well captured in these diffusion models. Yeah, the last one I think is a criticism of maybe a subset of diffusion models where you freeze the attributes of a new technology at the time of the introduction. But as you know, like a technology can change a lot over the course of how it's being adopted into a population. And so there are definitely some models which will allow you to sort of simultaneously change technology attributes over time. But I would say a lot of the sort of simpler ones don't do this, but that's actually maybe even a feature as opposed to something that's wrong with the model. So if we think about, let's say, a Bass diffusion model, for example, and I have some technology, right? There's nothing in here about how the technology is changing, right? And so let's say something I work on, like electric vehicles, right? It doesn't say anything about how the range is improving or how the efficiencies are changing or how it's getting cheaper, right? It's just literally, you got this technology and people will want it in a certain way, and that's gonna describe the curve. And so a little bit more simplified. And if you had the generalized form and you decided to, okay, I want to add all these things. I want to add the range, I want to add the efficiency, and I want to add things about the price of the vehicle. You could do that, but what does that mean? That means that if I wanted to do this forecast out into the future, now I also have to make assumptions about how all of those things that I included in the model are now changing, right? Now I have to say, okay, in 10 years into the future, I want to know what my adoption is going to be, so I need to think about what the ranges are going to look like 10 years in the future. I need to think about what the efficiencies are going to look like 10 years in the future, and so on, right? And so that may better describe kind of a relationship between those attributes and the technology adoption, but compare that to the simple example here, where the only thing I need to know is t, right? And so I just plug in t, I have my p, q, and m already calibrated. I don't need to do anything else, right? And so there's this kind of trade-off for this last particular point that, yeah, we don't include attributes of the technology, but that can actually make things a lot more convenient for us to be able to do these forecasts in the future. Okay. Any questions about that? Okay, the last thing that I'll talk about is something a little bit different. We're going to jump back to sort of right at the beginning. I was talking about, different forecasting methods, right? And so we've talked about our time series methods. We talked about some of these econometric approaches, and I consider like this, like the experience curve stuff, the diffusion of innovation stuff as kind of more in the econometric-y camp, right? Because these are looking at functional forms that have been kind of described as like based on real theoretical relationships. So thinking about those particular examples is falling into this bucket. I just wanted to, we're the last one, simulation end use, where we're making assumptions and doing some kind of simulation as more of a bottom-up approach, where it's more based on trying to construct models based off of how we think the world works, as opposed to like looking at data and using that to extrapolate trends. We're gonna give more examples of this in a little bit, but one that I thought might be interesting to talk about is actually related to optimization. So in the sort of simulation world, there is this thing where you're doing something known as model predictive control. So this is a particular example in kind of our modeling simulation world, where I am thinking about past states to inform the future in some way. So I'll describe a system. You have some different states X and controls U, right? And so for like a train, you might have a position and velocity that correspond to the state, and then you have some control of, let's say, the acceleration. Right? For a power plant, right, this might relate to operational attributes of the generator and turbine. So rotational speed, temperature, and power. With these things, I can tell you about how the system is operating, and then I have control over, let's say, the flow rate of fluid through the turbine, right? And then I can use that to control the states of my system. So a non-predictive controller is going to use information about my current and past state values to produce a control. A predictive controller is going to use those values to predict future state values, but then I'm going to use that to then produce a control for another sort of time step, right? And so you are able to anticipate the future farther along than sort of a non-predictive controller, because I'm using my forecasting elements in order to make future predictions of what I need to do. So a model predictive controller is essentially the mathematical description of doing this predictive control. And there are some questions of like, how good does that model need to be? How much farther into the future do we need to predict? And kind of what happens if our predictions are bad, right? And so as you get closer and closer to a predicted future, you can continually update your predictions in a way to like modify modify your controls. Yeah, so this is an example that being able to do some of this predictive control can actually provide a huge amount of benefit, even if my prediction isn't like stupendously good, right? Or even if your prediction horizon isn't really that far out into the future. Yeah, and so this is, we'll kind of go backwards here. Our cumulative fuel production or consumption. This is an example of model predictive control being applied to a vehicle, and essentially how you are operating the vehicle across different sort of velocity traces to be able to conserve fuel. And so in baseline, that's blue, and then with our model predictive controllers, which are in black and green, you can see you are essentially able to consume less fuel just by knowing a little bit into the future and predicting what you kind of need to do. Yeah, and so qualitatively, this is just showing this example of like this is something that might be used in like an optimization setting, where as you optimize, you're actually looping back in your optimization to like optimize out into the future some amount of time, and then as you move through time into your predictive zones, you're like updating your predictions and like re-optimizing. And so this can be useful for a lot of things where you need to anticipate something happening. Okay, and so kind of across this like set of different tools, there are lots of different ways that we make these forecasts, right? And they can be used for a number of different purposes. For something like MPC, that might be a little bit more sort of discrete. Oftentimes these are in reference to controllers, but this technique can be used for, even in use for something like energy systems, where you do have some kind of control over your system. And that's our kind of simple example in the sort of simulation world, but we'll talk about a little bit more once we look at a couple other sort of examples of real systems models. And then all of this econometric and regression stuff, that's a way for us to sort of understand that we can rely on historical and past data to like make better inferences about the future than sort of just relying on, I don't know, intuition or making it up. Great. Any questions about any of this stuff? Okay, that's it for today. So we'll end here, but I'm gonna stick around if other folks want to talk about projects. And so remember the proposals are due Friday, right? And if anyone has any last minute questions on homeworks, I'm also happy to help on that. And that, I believe, is due today? Or Monday, yes, right.